Well, hello again everybody, and it's a few days later and I'm afraid that I've got a bit of a bad cold, so if I sound very croaky, that is the reason. So I'm probably going to try not to speak very much today. So this board that I'm holding here, this is the amplifier board, and in fact I've just spotted it says on it there, that's the amplifier board. So what this does, it takes the input from the BNC connector on the front of the instrument, and it amplifies the signal, and it does some signal conditioning as well. Now, I've been having some problems actually trying to get an actual signal to measure, to count off, injected into this piece of equipment. So I went ahead and first of all I just tried the obvious things like testing some of the capacitors, and I tested 2 or 3 of them, and although the ESR value seemed reasonable, they were all about 50% in tolerance over on capacitance, so they'd all gone very high in capacitance, which probably does mean that these were on the way out. So having tested 2 or 3 of them, I've just bulk changed them, so these all been swapped out for new capacitors now. So I did that and I still couldn't get a signal out of this input amplifier, so I've traced it through a little bit further. Now on the front of the instrument, I think you'll probably remember there's a selector switch here, and it's a selector switch for the attenuation range. So there's a little bit of another little board which sits at the front here. You'll probably remember that it had this selector switch on it before that was totally jammed, and you can probably still see it's a little bit rusty on the outside. Well, I had to take everything apart to get this input attenuator off, but having done that I've managed to squirt some deoxit inside it, so hopefully we should be able to reassemble that. There's really not a lot on this board. There's a couple of capacitors and some resistors which are attenuators, and I've gone ahead and I've just quickly tested these. The capacitors are quite low value, and we've got another one here which I think is probably a polyester, although it's got a line on it. I don't think that's an electrolytic. It's 0.015 microfarad at 400 volts, so I'm guessing that's maybe a polyester of something like that anyway. But it tests okay, so I don't suspect anything wrong with that. So what I think I'm going to do is, now we've cleaned the switch, we should be able to go ahead and reinstall this, connect it to its BNC, and we'll squirt a signal into it, and hopefully we should be able to see something coming out on the oscilloscope and see that this input attenuator is actually working. So let me reassemble that. So I'm hoping you can see these 2 pigtails here from the BNC connector, and we're just going to pull these over these connecting posts and solder them back down. Now I'm sure that some of you will remember in last week's video, the first time that I actually connected this timer counter to the main supply, I actually used a lamp limiter to actually limit the current being supplied to this timer counter, because I thought that it's possible that we could have had a fault. Now I'm sure that a lot of you will be very familiar with the use of lamp limiters, but it's fair to say that they're more normally used with stuff like valve radios and valve power supplies. Now one of our regular subscribers, Hugo, he actually wanted me to just discuss the limitations of actually using a lamp limiter, and maybe just discuss why it's not such a good idea to use it on such a solid state piece of equipment as this timer counter. So when I use a lamp limiter, it's fairly typical to use a 100-watt bulb, but you can use different sizes of bulb to actually limit the current, but in this case I'm using a 100-watt bulb, so we can actually give an approximate value for what the current will be, and it's this little formula here. So if you know the wattage of your bulb, which in our case is 100, and you know the voltage, well, the AC supply here in the UK is 230 volt, so you take 100 watts, divide that by 230, and that gives us an approximate value of 0.43 amps. So for a lamp limiter, when we use this to limit the current to a valve radio, the current will be limited to a maximum of 0.43 amps. In the case of a valve radio, we have a transformer, it's got a total short circuit across the primary. The current to that transformer cannot exceed 0.43 amps because it's going to be limited by the lamp limiter. The bulb will glow very brightly and the current will be limited to 0.43 amps. And we actually saw that when we were doing the testing with our little counter, well, the first time I switched it on, my light bulb fully lit up, so you could tell that for some reason there was a hard short circuit across our timer counter main supply. So the drawing on the top here shows how we could use our lamp limiter to protect, for example, the transformer in a typical valve radio. Now in a typical valve radio we'd probably have 230 volts on the primary, and then maybe on the secondary we'd have 150 volts. Now I'm just making up these numbers to give you an example. What we can then do is, if we get a short circuit on the secondary of our transformer, we can actually work out what the current would be. So we know that the maximum current on the input here, the very maximum current that the lamp limiter will allow to flow, is 0.43 amps. And we use this little formula here, so the current in our primary of our transformer, we say that that was limited to 0.43 amps. So our secondary current would be 1.53, which is our winding ratio, multiplied by 0.43, and that equals 0.65 amps. Even if we had a dead short across our secondary here, the very maximum current that we could flow is actually only 0.65 amps. Now the reality is it would be much less than this, because we've actually got a number of inefficiencies in the transformer, and both of these windings have also got a resistance and impedance, so you would never actually see 0.65 amps, it would be lower than that. Now the problem which I think Hugo was really trying to warn me about is when you're actually using a digital circuit, you're not using an output voltage from your transformer of 150 volts. Maybe you've got 5 volt logic, so maybe typically your output from your transformer will be 6 volts. So it's 230 to 6 volts. So our transformer ratio, our winding ratio, it's approximately 38 to 1. So the problem is here that the input current hasn't changed. If we short circuit our secondary, the maximum input current, it's going to be limited by the lamp limiter. So again, it's only 0.43 amps. But the problem when we do the formula this time is that we've got this much bigger turns ratio. So we've got a current magnification of 38 times our primary current, which is 0.43 amps. So that actually means that in theory we could have fault current of 16 amps flowing in our secondary of our transformer. Now again, this isn't a true figure, it would be much lower than that because of the inefficiency on the transformer and because of the impedance of the windings. However, it could still be quite a high value on our secondary of our transformer. Now you've got to remember that semiconductor devices, they're actually only designed to work at milliamps, and in fact many cases microamps. So if you start connecting a 10 amp supply to them, the reality is you're going to destroy them instantly. So what Hugo is saying, that the use of a lamp limiter for protecting solid state circuits, it's maybe not such a good idea. And I actually fully understand that, and I agree with Hugo, but I would actually also say that a lamp limiter will potentially still give you some protection against transformer faults, and they're also quite useful to use when you're testing things like switch mode power supplies where you can't slowly wind up the power using a variac. So thanks very much, Hugo. That is a timely warning, and it's also something to take note of, because certainly something that I hadn't really considered before Hugo mentioned it.
Stop that! Silly! And it's softly coming.
So I'm hoping you'll be able to see this is the input attenuator board that I've just reinstalled, and it really is quite crudely manufactured. But unfortunately, as I was reassembling it, one of the circuit traces fell off, and I think it might have been broken previously, so that could be the reason why we were having problems getting an input signal from the BNC. So what I've done is I've just taken a piece of link wire there, and I've put a bodge wire into one of the pins on one of the back of the components. So hopefully we should see an input signal coming in now. So I think before I go ahead and reconnect this input amplifier to our little attenuator board, I'm just going to see if we are getting a signal out of it now, because originally I wasn't getting anything out of it. So I'm just connecting a signal generator to the front input. I'm just going to have a poke around with the scope and see if we can find anything. So that's our input signal there, and on my scope I can see a nice sine wave. Just check that it's coming through the bodge wire that we put in, which onto the trace, which it is. you can see that it does actually increase the gain slightly, as you would expect the attenuator to. But this middle setting here, it's just the same as the 1 volt setting, so there doesn't seem to be any difference between the 1 volt range and the 100 millivolt range. And sometimes it does seem to give you an extra bit of attenuation, but it kind of comes and goes. So I'm afraid I'm diagnosing this as a switch fault. Unfortunately, I don't have another of these slider switches to replace it with, so I'm afraid I'm going to have to leave this as it is until we can get a switch and just crack on with something else. So as you can see, I've gone ahead and I've installed our attenuator board, and it's connected to the amplifier and signal conditioning board here. So we get an input from the BNC here from the front of the instrument. The signal gets amplified and then it goes to the counter circuit via a coaxial cable here. So rather than doing all that tedious fault finding between this end and this end, what I've just done is I've injected a signal into the front of this counter, and I've checked that the signal's coming in here, and then went straight to the output of this board to have a look for the output from it, and unfortunately and rather sadly didn't get anything out of it. So as a general rule, what I would start doing now is, with our signal injected at the front end of the amplifier here, we would actually work our way from the input to the output and look for our signal to disappear. But this circuit board also has a couple of power supplies on it, and you must never forget that really important rule: thou shalt check power supplies. So we've got a 5 volt power supply here and also a 15 volt one. So I went ahead and checked both these, and the 5 volt was fine, but unfortunately the 15 volt rail, which I've disconnected, that didn't have anything at all on it. So we've got a problem with this 15 volt supply. So the wire for our 15 volt supply, it goes into a wiring loom, so let me just turn the piece of equipment over. Now I can see that our wire for our 15 volt supply, it comes up here somewhere in this wiring loom, and what we're looking for is, well, it's pink and brown, and well, I'm sure you can make your own joke there. So we're looking for a pink or brown wire, and of course I was looking for that 15 volt supply down here somewhere, because we've got things like 16 volts, we've got 3.8 volts, we've got 5 volts, and because it was feeding a fairly precise input signal amplifier, again I was expecting it to be down here in a nice low voltage part of the circuit, and I spent quite a lot of time looking for this 15 volt supply and I couldn't actually find it. And eventually I did manage to catch sight of this wire by, just trying to spot it in the wiring loom here, and it actually comes up here to the 175 volt section. I'm not sure if you're going to see it, but here it is. There's the pink and brown wire. It's plus 15 volts, and you can see it's right adjacent to this 175 volt rail, and this is actually that's AC, so by the time you actually rectify that, we're talking around 250 volts at this part of the circuit. So they actually derive out their plus 15 volts from a supply of around 250 volts DC, and I've got to admit I'm not really sure why they've done that. The only reason that I can think of is that they wanted a very clean supply which was on a separate transformer winding to the lower voltage supplies here, which is full of all the counting logic. So all the low voltage stuff, the 12 volt rail and the 5 volt rail, that's actually derived from, well, we've got a 12 volt tapping on the transformer and also another 10 volt tapping. So I've assumed that they've actually derived the logic supplies from those. So maybe they wanted a very clean supply, but to me it makes absolutely no sense to go from 250 volt right down to 15 volts. That's a really big step, and of course you've got to dissipate all that wasted power somewhere, and the way they do that is in these two big resistors here. The number of them, for those playing along at home, is I think it's R3 and R2. Now one thing that I have noticed is, since we've actually gone ahead and replaced the capacitors, while I've been testing and working on this, I've managed to give myself quite a few little electric shocks, because these capacitors, even when I switch the piece of equipment off, they're actually holding their charge, and I managed to fry myself quite a few times. So we've got our transformer here with its 175 volt output. Well, it should be 175 volts, but my main supply here is very high. It's probably above 250 volts today, so this is probably going to be closer to 200. Probably help if we put it on the right setting, AC. Okay, 200 volts. And then that 200 volt rail, I think it comes up onto this fuse here, which it does. And then somewhere up here, I've traced it through somewhere. I think that's the, I think this diode here is the half wave rectifier. So now we've got our 233 volts, and that'll be half wave DC. And then that half wave DC gets smoothed by, I think it's this capacitor here. So there's our 234 volts. And then it goes on to these two series resistors, these big power resistors that we mentioned earlier. And I think it actually goes into that one first. So there's 234 coming out of it. The other side of this resistor, 233. But the other side of the resistor, we've got nothing. So this resistor here, this is the one that's going to feed our Zener regulator, which is actually down here. They've given it the number MR6, this little black thing. So if we go on our Zener regulator, well, it's showing the meter's just pulsing around 2.6 volts, but it's not 20 volts, is it? So it could be two things. One, this diode here could have gone short circuit, which is one of the failure modes, or one of these, well, this 15k resistor's gone open circuit. So let's just switch off. Now I need to actually discharge some of these capacitors, because I've had a whole range of interesting electric shocks off this thing since we actually started putting these new capacitors in. They've actually done their job. So even though this is turned off and unplugged, we've still got a capacitor charged up here with 180 volts on it, and I can promise you, having touched it quite a few times, it's not a lot of fun. So we're going to have to just discharge them. So that's taken that one down. Okay, that's fine. Yes, I've had a few tickles off this board. So we've either got this Zener is either short circuit here and clamping our voltage at 0, or this resistor is open circuit. Now both these resistors are stone cold, so they're not drawing current. So this Zener isn't open, is open circuit. It's not closed. If this was closed circuit, these resistors here I'd just burn a hole in my finger in them, because all that power would be dissipated in these two power resistors. It isn't, so one of these is open circuit. I do apologise, you can tell I'm really struggling through here. I'm losing my voice quite badly. So let's check this one first. What is that? That's brown, green, orange. So yeah, that's 15k, isn't it? Got 15k there. And the one next to it is reading open circuit. So I think there's something wrong with that. Let's whip it out. Now unfortunately I haven't got a power resistor as big as this. I don't know if they're 3-4 watts, something like that. So what I've actually had to do is I've got two 7k resistors, which I think they're about 2 watts each, and I'm going to bodge them in for now. The main reason I'm using these is because I haven't got anything bigger, so we'll have to give it a go. So we've got our two power resistors at the top of the board here, and you can see that they've actually been installed with these little ceramic standoffs on the legs. So the reason for them is the designers know that these resistors are going to get damn hot. So they actually want to lift the resistors away from the board slightly, so they can get a little bit of better airflow under them, so they can actually cool from all sides. And the other reason they've done it is they actually don't want them to get so hot that they're going to start burning or damaging the fiberglass material. So that's what these little white things are on the legs, if you've not seen them before. They're just ceramic standoffs. I do hate it when they actually bend the legs over on resistors and things like that, components. Of course, it's done the usual thing, because the legs are bent over. I have managed to damage the circuit board trying to get them out, which I keep doing. Now of course we've got this resistor out of circuit, we may as well just go and double check it. Yeah, that's reading open circuit, so in theory we should have, I think we wanted 15, I think I've actually installed about 16k. So our new resistor, it's going to measure about 16k, which it does. Now I'm pretty sure that the only thing that's actually on this 15 volt supply rail is that one input amplifier board. So I've actually got the input amplifier disconnected at the moment, so I think I'm actually just going to throw caution to the wind and switch it on and see what we actually get. So let's check our output for our 15 volt rail, see if we've got anything like. Well, the answer is no. Well, that didn't work, did it? Well, I'm not sure if you've seen one of these before, but this is for testing Zener diodes, and it's made by the Peak Atlas company. It won't test any Zener diode, but it will test any up to 50 volts. So I've removed the Zener from circuit, and I was really expecting it to be a short circuit or something like that, because we weren't getting any output from our little shunt regulator. But if I actually just test this Zener diode, it's coming up with a Zener voltage of 19.64 volts. So it's working perfectly. So, well, as it turns out, I've just been on a little detour to Planet Shenanigans. You saw that one of these resistors had failed before, and I actually changed it out, and it was open circuit. Now the one next to it was measuring 15k, which it should do, so it was working perfectly. So we went ahead and tested our circuit, and I was getting all these strange readings. Well, I can't really explain it, but it turns out that both these resistors were bad. So having changed one of them out, I've now gone ahead and have changed the other one out. Because, you know, it failed. But I definitely did check this resistor previously, and it was measuring good, so yeah, I'm a bit surprised. And I did go up, before I removed it, I did go over the circuit board looking for dry joints and stuff like that. But yeah, it's definitely bad, so I can't really explain that. Anyway, I'm hoping when we put this Zener diode back in here that we're going to find everything works again. Fingers crossed. As you can also see on the bench, I've gone ahead and I've set the variac up because I'd removed this diode from circuit. I did actually power it up, but without this Zener shunt regulator, I'd have been getting a high voltage across the 15 volt rail. So I've turned the voltage right down to just a few volts. And that allowed me to put some voltage on the circuit and actually trace it through with the Zener removed. So we've got 20 volts on our main smoothing now. And we've now got 19.275 on our 15 volt output. Well, it says 15 volts, but in other places on this circuit board it's marked as 20 volts, so I don't know why it says 15, because it's definitely 20 volt Zener. If we turn the voltage up, that Zener voltage should stay relatively constant, which it is. So we've now got our 15 volt rail back. So that really was, for me, an interesting little deviation to Planet Shenanigans. Wasn't expecting to be going there today. Right, I'm just going to get rid of this variac and power it up on full power and check the 15 volt rail again. Okay, I'm connected up to our 15 volt rail now, so if all's good we should have 15 volts when I put the full power on. Well, 15, sorry, it's a 20 volt rail, isn't it? I'm going to leave this on for a few moments and see if those resistors are actually getting warm. I suppose if I could be bothered I could do the maths, but I can't. Easier to put my finger on. Right, turn that off and discharge those big capacitors, sorry. Discharged. No, they're stone cold, so they're okay. So in theory now I can connect my 15 volt supply back to my circuit board down here, and back to the point where we were before, where I'm going to hopefully power up this input amplifier card. So are we going to have our full 20 volts in our input card now? Let's see. We have. And let's just try a quick test of trying to put a signal into it. I'm not particularly hopeful, but let's have a go before we get the scope out. Well, as you can see, we now have our counter counting in fact. And just to prove that we are actually counting this input and it's not the internal time base like we had before, no shenanigans. There we go. So I've just disconnected my signal generator and reconnect it. And I think I've got a frequency there of 1 kilohertz. So let's try slowing it down a bit. I'm going to go for 100 hertz maybe. Okay, so I've got it counting at 1 hertz now. It does appear it's quite sensitive, so this input attenuator is working. It's just kind of lost its indexing, so you know, normally than clicking into each position, it kind of clicks into the end positions, but the middle, it doesn't click, so just got to position it right. So I've now positioned it in the middle, and well, as you can see, it's counting now.